Hey, good afternoon. So I realize this is the session that stands between you and some beer and some dinner. So I'll try to make it as entertaining and interesting as possible. So this session, by the way, about getting secure in the cloud versus on-prem. There's only one answer to that. You need to get to the cloud. If you're on-prem, you're going to get hacked. It's just a question of time. I'm serious. This is getting, the pressure on security getting increasingly high, and it's getting harder and harder for an organization to get secure by themselves in an on-prem setting. And you should really leave that to the people who know about it. And as Ed and Omer showed you before, there's so much thing invested in the cloud for security. There's no way that you can, even expect to reach that level of security. So get to the cloud. In this session, let's get back to AI now. So this session, I just a fair warning, is going to be non-technical sessions. There's not a lot of coding in it, and not at all actually. But I think, yeah, it's okay. It's okay to leave. So I thought I wanted to talk a little bit about AI in a broader perspective. I'm not even going to talk very much about BC in that session. I'll talk a little bit about how we made agents. If you haven't attended the session about our agents by Christian and Omer, Christian, Esteban and Erica, if you have seen that session, that's going to be kind of a very short repeat of that. And if you haven't, that will give you a little bit of insight in how we build agents. But I wanted to basically take a step back and clarify a few things around AI, because everybody's talking about it. It's going really, really fast. There's a lot of terminology out there. And talking about terminology, I will start with that. So I showed that slide already, I think last year at TechDays. So you raise your hand if you remember it. Had a slide about terminology. That's fine. Nobody remembers it. That's cool. One people. So I'll go through it again because I think this is important. So what is artificial intelligence? Artificial intelligence is a lot of things. We say AI these days. People are saying AI all the time, and using it in all sorts of context. And artificial intelligence is actually an old science. It's not new, and it started. I think. Let me take a look at my notes here. I think if you look it up, the term AI was first time coined by a guy called John McCarthy at the Dartmouth conference in 1956. So that's how old the concept of artificial intelligence is. In 1950, even before that, before the term artificial intelligence was used, Alan Turing, who is considered the father of computer science by many, imagined the Turing test. Already back then in 1950, he had this vision of machines being, as intelligent as people, and he devised, you have probably heard of it, the Turing test, which is a test aiming at determining whether you are interacting with a machine or a human. If you haven't seen the movie, by the way, it's called The Imitation Game. It's a pretty good movie about the life of Alan Turing, and specifically about his work on cryptography during the war. And then in 1952, there was the first machine learning program, a self-learning chess program, which was built by Arthur Samuel. And in 1951, the first neural network computer were invented by, established by a couple of guys called Marvin Minsky and Dean Edmonds. So this is just to say artificial intelligence is not new. But then it becomes really interesting in the 90s, because in the 90s there's the first occurrence of what's called machine learning. So what's machine learning? The very first attempt of artificial intelligence, there was mostly rule-based, what we call rule-based systems, where you have like basically a rule engine. And they were trying to, with this rule engine, try to simulate what a human would be doing. I don't think there is much going on in that area anymore, but it's still considered being part of artificial intelligence. And there was classic computer system, computer vision system already there. People were trying to do something with cameras and try to recognize what's on pictures already back then. But this was pretty much, everything was pretty much algorithmic based. So somebody somewhere was writing algorithms pretty much like you do today in traditional programming. And then in the 80s, machine learning appeared. So the difference with machine learning and traditional algorithm based, you actually don't write a program in a traditional sense. Machine learning is about, as I'm sure you've heard, having a lot of data, and you have some data and trying to find patterns, and so you typically have a lot of data and you know what the output should be. So you have a lot of input and you know what's the right output and you feed it to a machine and let the machine determine what the algorithm is. So you don't write the algorithm, but you train the machine to figure out what the algorithm is. And the magic in that is, if you have not very many data, imagine a table with a certain number of columns. If you have 2 or 3 columns, then it's pretty easy for a human to figure out what the algorithm should be. You can see kind of the pattern in it, and with a lot of if, then else statements, you can kind of code this algorithm. But as soon as you have a large number, imagine you have a very large number of parameters, also called features in machine learning language. Like let's say you have hundreds of them, and they all vary, and depending on this combination of parameters, you have a different output. Then that becomes really, really hard for a human to actually design the algorithm that would do that. And that's what machine learning does. That's the magic of machine learning, right? So you train a model into basically generating the algorithm. And then within machine learning, there is deep learning. So deep learning is even more magical in that sense that with machine learning, traditional machine learning, which is not deep learning, you have kind of an idea of what the rules are. And you kind of, tell the model this is how you should build the algorithm. You don't tell what the algorithm, but you have some rules, right? Whereas in deep learning, you don't do any of that. You have a neural network. You just tell the machine this is the output that's expected. And before I continue with this terminology slide, I want to do a kind of digression on this. If you haven't read that book, there's a guy called Ray Solomon, and he was part of this company called DeepMind, and he's wrote a book recently called The Next Wave, where he's talking about AI. And it's a really good book. If you want to read, I really recommend you read it. And so he's talking about his journey and what they were doing at DeepMind. They were actually working a lot with neural network, and they were using games, and basically that was the era after the chess game. So what happened in history was the chess game was one of the first games that the people were researching artificial intelligence used as a use case, because it was considered a pretty complicated game, right? And there was this turning point where I don't remember the date, but I think I have it in my notes. In 1997, Deep Blue, which was a program written by IBM, actually beat one of the world champions, Kasparov Wajdi, one of the best players in the world at chess. And it actually was not like there were 6 games, and there was 3 draws and 2 wins. So it was not like, it's just beat the crap out of him. So it was really a tight race between Kasparov and Deep Blue. So when that was done, then the researchers they turned to other problems, because actually at the same time, computing power became more and more available and cheaper, and you can have a lot of computing power. And some of the ways that these chess machine learning chess games were working, they were using a lot of what you could call brute force. They were basically trying to calculate all the possible combination and determine what the best combination was. And the thing with chess is that it doesn't have that many combinations. Chess has an estimated number of combination of 10 to the potent of to the exponent of 123. It's a pretty big number. You know, it's a 1 with 123 zeros, but it's still not very big, you know, compared to how the computing power has evolved these days. So using brute force became, you know, less and less interesting in terms of artificial intelligence, and that's why researchers turned to another game, which is the game of Go. It's come from Asia, and this is the reason why it's interesting is because the rules are quite simple, but the number of combination is, you know, let me look at my note, is like way bigger. It's estimated to be between 10 to the power of 170 to 10 to the power of 360. So that's a difference of about 10 to the power of 47. You know, I don't know if you can imagine. This is really big numbers. You start to be there where you have a hard time to relate to that. And clearly, the brute force approach doesn't work for these kind of games. So getting back to DeepMind and what this company did, they started looking at these games and started looking at Go, but they didn't start with Go, which is kind of complicated. They started with simpler game. Like back in the 80s, they looked at, in the 90s, they looked at video games like Breakout, for example. And so if you're not familiar with this game, that's a video game. You have the racket at the bottom, and you have a ball, and you need to break all the bricks here by sending the ball. So what Mustafa Suleyman wrote in his book is that there was two key moments in his journey working with AI, and one was, when he was training, they were training that the model to play that game. And so he was deep learning. So the only thing they did, the only thing you do when you're deep learning like this, you say, okay, here's the racket. You can move it to the left or to the right. That's what you can do. And your goal is to maximize your score. That's all. That's all you tell the model. And then you let the model play. And what happens is that the model will try moving randomly at the start, and score 0, obviously, because he will miss the ball. And then, probably at some stage, randomly, he will hit the ball, and he will make a few points. Then the model will realize, okay, when I do that, when I hit the ball, I make points. So what he's going to do as next, he's going to try to hit the ball more. And of course, he's going to realize that, okay, I make more points when I hit the ball. And then you train it like this, and the great thing about that kind of training is that you can just let it run. It doesn't require. It's called unsupervised training. You can just set it to run and come back in a month, and eventually you'll have a model, right? So that's a pretty practical way to do machine learning and deep learning. But then what happened was that what they figured out that this model figured out that actually if you keep hitting on the side and create a corridor here, where you open all the bricks here and send the ball behind, then the ball will go and hit all the bricks, and that was a really good strategy to make a high score, right? So the model consistently was trying to do that because it figured out that was a good strategy. And the reason why Mustafa Suleyman think that was a turning point and a milestone in the history of AI is because this strategy, if you ask a human who, with an advanced player of that game, who has played that game a lot, they will tell you, oh yeah, we know about that strategy. We know about that. That's how you play the game. That's how you try to get a high score. You make a hole in the side and you send the ball behind. So what's interesting about that is that in that instance, the model actually reached a strategy which is the strategy that human also had figured out, right? So which is pretty significant when you think about it. And another decisive moment was with AlphaGo. So AlphaGo was, again, a model that DeepMind had trained to play this game of Go. And they went to, I believe it was Korea, to compete against some of the world champion in Go. And this is, again, these guys are really smart, and they train a lot. This is like a sport. And in Asia, it's really big. There's like people commenting. There's a lot of audience. And the machine was, so this model were playing against one of the world champion, and what happens there is, it's a tournament, so there's several games, and the model won the first game, not so surprising, and then in the second game, there is the famous Move 37. And you can look it up. Everybody knows about the Move 37. And what happened is that in 37 moves of the game, the machine, the model, made a move which everybody thought was a stupid move. Nobody understood why the model did that. And the people, the commentators and the public, they all went, "Oh, that's it. The model is just, made a mistake. It's going to lose," because it looks like really a stupid move. But then the player, who's one of the world champion, that didn't think exactly that was such a stupid move, and it took a really long time to play again to respond to that move. And actually, the story says he just actually stood up and went out and came back. And it turned out, after 10 or something moves after that, it turned out this move was really, really clever. And the model ended up winning against that player. And the reason why it's an interesting milestone too is because in that instance, the model actually figured out a strategy that no human had thought about before. That was kind of a new strategy. There's a lot of strategy known in Go because people are studying them. It's like in chess, people are studying these strategies. And for the first time in history, a machine actually was, you can say, clever, more clever than a human. So that was a digression about this, but I just thought it was interesting to mention this thing which historically had some significance in the world of AI. So let's get back to the terminology. So deep learning, getting the model to the neural network to again determine the algorithm just by based on data and just what expected result and with no preset rule. And then within deep learning, there's this thing called generative AI. So that's what everybody's talking about today. And a lot of people today, when they say AI, when we talk about AI, they actually mean generative AI. So generative AI, it's about, just to be clear, as the name says, it's about producing new content. For example, images, text, music. So there are models. Everybody is talking about often about large language models, which are about generating text, but there's also, as you know, models to generate images, but there are also models to generate music, text, and music, and all sorts of things. So this is generative AI, and again, within generative AI, there's large language model LLMs, which is yet a subset of generative AI. So as you can see, there's a lot of things within AI, and even if today large language models have a big place on the scene, the rest of the AI is not dead. Like for example, when we talk about self-driving cars, we know that there's a lot of AI in self-driving cars. It's not generative AI. You don't want to generate new content, right? Our self-driving cars try to do is that given an input, like from a camera or sensors, try to determine what to do with the brake, the wheel and the accelerator, things like that. But you don't want it to be like creative and generate some new things, right? So this is not a generative AI problem, but it's still a very interesting and relevant problem. AI problem, right? All right. So, and yeah, I need to say that. Then there's Microsoft Copilot. Just to confuse everybody, there's this term Copilot that we use at Microsoft. Just to be clear, Copilot is a brand. It's not a technology per se. So it's basically an umbrella over a whole bunch of technologies that we have at Microsoft, right? So we have Chat Copilot, we have generative AI for pictures. It all comes under, agents. It all comes under the Microsoft Copilot brand. But just to be clear, this is not one particular technology as such. It's just a brand name. So I hope that clarifies a few things here. All right, so let's talk about language models now, because this is obviously the talk of the town. This is what everybody is talking about. And I'm going to talk about large language models and small language models a little bit here. But first, a few examples of models. And so I'm sure you're familiar with some of these. So there are models like GPT-4o, It has 200 billion parameters. I'll get back to what that means, because you might have heard about it. People talk about, about models in terms of what size they have. Is that a big model, small model? And what it means is how many parameters they have, and I'll get back to what that means. So 4.0 Mini is a reduced version of 4.0. It's at only 8 billion parameters. And you have a very, very large model, GPT-4.5. It's one of the largest models available today, at least in the commercial realm. It has an estimate. So these numbers now, past GPT-4.0, they are more or less estimated, because OpenAI got a little bit secretive about how many parameters they have in their model. So these are not quite public, but there's a lot of people, estimating these things, and it just doesn't matter whether it's 5 or 7 trillion. It's just to have an idea of the magnitude of this model. So the GPT-4.5 is a huge model, as you can see, compared to the other one. And actually, I think it's going to be retired by OpenAI, because it's just simply too expensive to run this model. And they made so much progress with other type of models that they're going to discontinue it. GPT-01, which is a reasoning model, so it's been specifically trained to be good at reasoning, has 15 billion parameters. And then you have models like 5.4, which is a Microsoft model. It's a small model with only 40 billion parameter. And then another model that has been a lot in the news, I'm sure you have heard, is coming from China, is a DeepSeek Air 1. It has 671 billion parameters. So the way small models are made, no, sorry, I need to point there. You can't see if I point out there. So the trick with making small models, I'll get back to small models in a minute. But the trick is, so I'm sure what's used to train this model is the internet. So you've probably heard that the language model, they are trained on the whole internet. So first of all, that's not entirely true. It's not like you take a model and let it loose on the internet and go and train, right? Because there's a lot of, simply because of the fact that there's a lot of content on the internet that you don't want your model to train on. I don't need to go into details, but I'm sure if you go a little bit on the internet, you often stumble across things that you don't want to be, you have part of your training. So what people are doing when train this model, they take basically a curated version of the internet. So they remove something, things like, that could be, hateful, things that with, sexual content, things, harmful things, things with racistic content. All these things are curated and removed from the internet before these models are trained locally. And the idea with small language model was that, okay, maybe we don't, so the idea was, okay, the internet contains a lot of, even if you curate it, it contains also a lot of crap and a lot of, less quality content. So instead of training on everything, let's try to pick a subset of this training set, which is a good quality, and train a model on that. And that's basically the principle behind small language model. So the idea was take things like for textbooks, Wikipedia, things with relatively high quality content, and train this model on that, and that allows you to make models that are much smaller and can run on smaller, much less hardware. I'll get back to that in a second. So I've been talking about training and parameters, right? And you've probably heard a lot about this as well. So what does that mean? First of all, let me say, it's very complicated. It's really a science that we should leave to the people who know what they're doing, right? For a small world, if you're working with BC, there's enough, work to do. Don't go into training. That's way too complicated. But just to understand a little bit what that means and what these parameters mean, let me make an analogy. Does anybody know what that is? Nobody? Okay, that's a synthesizer from, I think, from the 70s. So it's it was before the digital era of synthesizer. So it's a musical instrument, and you have all these buttons, and it's all analog, right? And you have all these buttons which are supposed to be, you're supposed to be able to emulate sounds from other instruments with that, right? Horns and violins and piano and stuff, right? And imagine you want to produce, you have this idea of a sound in your head, right? And you want to produce that particular sound. There's about 44 button and switches on that synthesizer here, right? And sorry. And then, so you will need to tweak and adjust each of the button to create until you reach the sound that you want, right? If you have this idea of a sound. So and this is pretty much the equivalent of having 44 parameters as an input, and you have an output that is the one you want to achieve, right? So this is training this is one row of training in your data, right? And then you'll have, and then you'll repeat that for another sound, right? Another output, and you have to readjust all the settings. And this is what training is. And the analogy of the buttons are the parameters. So when you talk about a model with 200 million parameters, that means there are 200 million buttons that the training needs to adjust until you get the expected output. So that's basically what's happening when it's very, very oversimplified, but the principle of it remains pretty much as I explained it here. So you have these 200 billion or something, or 200 million parameters, right, with that one output, and you're going to try all the combinations until you get the output you want, right? And then you repeat that for all the rows you have in your data, right? So this is what training does. So as you can imagine, this is very computer intensive, and it takes a long time, right? Just to give you a few examples. No, I get back to that later. I have some examples of how long time it takes to train these models. This is about this slide is about hardware because. Again, as I mentioned, this is very computer intensive, training these models. And I'm sure you have heard, that these models, they run on GPUs, which are originally graphical processor unit, but there's not much graphic going on in this. So this is a NVIDIA H200, which is one of the most advanced GPU these days. And just to give you an idea on that, this is one GPU, right? It looks like this, and it has something like about 1,700 CUDA cores. CUDA cores are, think about it as these are processors which are meant to run in a parallel architecture, and they are basically worker processor, and they are able to do a lot of operations in parallel. My laptop has 12 cores, just to for comparison, right? Which is a good laptop. And there's 528 tensor cores. These are other cores which are specialized for training. So these are mostly activated when you train models, as I mentioned before. And then there's like 141 gigabyte memory. This is all in one chip, right? 141 gigabyte memory on the chip as well. There's something about latency between the processor and the chip, which are relevant for how you can do the training. It's kind of very advanced. And then they consume about 700 watts, just one of these, right? So this is one H200, right? So models like GPT-4o requires 8 to 16 GPUs of the H200 to run. For a mini, can actually run on a single one. It's actually possible. And so GPT 4.5, as I mentioned before, is one of the largest models that exists. It requires 24 to 48 GPUs just to run. Right? But small models like GPT-01 and 5.4, you can run them on one GPU. And actually, if you have a decent graphic card at home, or Copilot Surface Plus, with a built-in GPU, you can actually run this model locally on your machine. They don't run very fast compared to when you use the cloud versions of them, but they do run, and you can do simple things like summarize this, summarize that. You get an answer, but it's not very fast, but it's possible. Okay, so training costs. So how much does that cost to train a model, a large language model? So GPT-2, which was on the early model, which has 1.5 billion parameters, costed about $50,000 in training. So that's the GPU time you're using, the power and the GPUs. Megatron Turing, which is another model. It's not an OpenAI model. It's a pretty large model. It has 530 billion parameters. The cost was $11 million to train that model. And GPT-4, from GPT 3.5, I think, and after that, again, OpenAI became a little bit secretive about how much training time they use and of the cost of it. But of course, when things get out on the internet, so there are some estimates. GPT-4 was trained for about 100 days. So, as I mentioned before, you go and let this model train, and that took about 100 days, about 3 months to train this model. And the estimated hardware utilization cost was about $63 million. So it's just to say, training a model is a kind of a complicated affair, and it's also very expensive, and it requires some infrastructures that most people don't have. So now let's look a little bit at small language models, because I think they are, everybody's talking about large language models, LLMs, but small language models are also, I think, really relevant and interesting for us in the context of Business Central. So they're much cheaper, obviously. Right? They are much faster. So if you use them for simple tasks, they will respond much faster than large language models. They're great for many tasks. Of course, if you have a very complicated task that requires a lot of reasoning, they might fall short. But if it's just do something like summarizing and things like that, they are really good at that. And so example of small models are 4.1 milli, 5.4, and they are much cheaper per token. So let's talk a little bit about tokens. Because you might have heard the terms as well. People talk about tokens and how many tokens there is. So tokens are basically prompts and replies are handled as tokens. And you can almost say that a word maps to a token. So one word, one token. Almost. It's not quite true, but as a rule of thumb, it's pretty much what it is. Some words don't. Some words requires more than one token. And for models like Azure OpenAI models, if you go directly to the model, I'm not talking about what we announced this morning at the keynote about agents. We have a different pricing model, but if you just go to Azure, create a deploy model, an Azure OpenAI model, you are going to pay per token consumption. And there's a difference in input tokens and output tokens. Output tokens, meaning the reply you get from LLM, are much more expensive than input tokens. If you want to know a little bit, so I have a very quick demo here, what tokens look like. There is this page on OpenAI, on the OpenAI website, which is a tokenizer. So you can enter a text here. This is let me type. This is a test, and it will show. You can see here in the underneath show you how does it get tokenized. Where's my laser? Here we go. How it gets tokenized here. So there is 5 tokens in this sentence, right? And actually, these tokens are converted to ideas, to numbers, and what happened after that is a lot of matrix calculation with this token that generate actually the output. So let me show you another example. If I add a thing, this is unpredictable, right? We can see here a couple of interesting things is that this and this here are not the same tokens for whatever reason. Don't ask me why. Unpredictable, for example, has 2 tokens here, as you can see. Even though if it's one word. And there are even sometimes very long words that tend to be broken down into 3 tokens. So if you want to see how many tokens there is in your prompt, you can use this tool. It will tell you exactly how many tokens you are going to pay for in your prompt, in your input prompt. And if you take some sample answer, that will tell you also how many output there is in your prompt. Let me get back to my presentation here. Yeah, all right. So some example of pricing, and these prices are per million tokens. So GPT-4o, you're going to pay $2.50 for 1 million input and $10 for output. There's a factor 4 between the replies you get, the output tokens and the input token. It's roughly, the same for all models. There's roughly a factor 4 between input and output. So if you think about it, when you do your prompt engineering, actually you can have if you have a much bigger input prompt and a smaller output prompt, it's actually a better deal. So in some scenario, it might be interesting to have a larger prompt as input and just have just answer true or false. And then you'll get a very small, output token, very few output tokens, which is, going to save you some money. So there's some things to, you can compromise with here. So 4o Mini is a lot cheaper. Again, that's a small language model I was mentioning before. They are much cheaper, only 15 cents and 60 cents for output tokens. O1, so we're getting into the more expensive model now. O1, which is the reasoning model, costs $15 per input token and $60 per output token. And whether O1 Mini costs only $3.50 and $13 as an output. But as you can see, GPT-4.5 is really, really expensive. It costs $75 for the 1 million input tokens and $150 for output tokens. So very expensive model. So you should only use it if you need something very, very complex. Actually, most of the tasks today, even if you have a quite complex tasks model like O1 and the new reasoning model, which is relatively cheaper, are pretty good at solving a lot of complex problems these days. Okay, a few words about agents. Agents are the new thing. We talked a lot about agents this morning at the keynote. There was this great session with Christian, Esteban, and Erika this afternoon, if you haven't seen it. Maybe you can see the recording. So agents are, obviously based and constructed and developed on top of generative AI. And what's specific with them is that they are, they can perform a task autonomously. And they're different from AI assistant and chatbot because they really have they have a purpose, they have a goal, and they are meant to do something very specific. And usually they can perform this task through multi-steps, and they're also capable of autonomous decision. They have agency, And I have a few minutes left, and I want to use that to give you a little bit of insight, if you haven't seen the whole presentation I was referring to, on how we build our agent platform in BC. So basically, what we're doing is that the principle of it for the sales order agent, for example, that we have 11 different prompts in our platform. And you can see we do a lot of things. We analyze the message, we summarize the steps, we execute the task, we have a task execution prompt, we generate reply, and so forth. Right? There's a loop detection prompt, which is trying to detect whether the agent is running in a loop and doing the same thing all the time. But the heart of the agent is the task execution. And what it is basically, the rest is kind of, the mechanics of the agent. It's important as well, but really the heart of it and the prompt we spend the most time on, I would argue, is the task execution prompt. And what does it do? And there's some review request and context validation, and there's some orchestration around this, right? So this task execution, the principle of it is, here's a page, we show the agent basically a representation of the page you are on. It's a JSON representation, but it's just a technicality. It could be HTML, right? And we show all the fields on the page, all the actions, and we give a bunch of functions that the agent can call. It's basically function calling prompt. And we say, okay, you can navigate to that page, to another page, you can click on these actions, you can fill data in these fields. These are basically the things you can do. There's a few more, but this is more or less what we say. And we actually, so we're asking that prompt, then we ask them, okay, given that page, and given the task, which is, for example, doing a sales order, and given that you have this possible action, what action should I take next? So if you're on the role center, if you start on the role center, the agent will probably go, okay, what's on the role center? Or is this action called sales order? I probably want to go there. So it's going to say, okay, click on sales order. And then, so we navigate to the sales order page, and then there's a list of sales order. And again, we do the same thing. We show the page with all the sales order, and show it to the agent, to the LLM, and with all the possible action, and ask again, okay, now that's the page, so what do I do now? And the agent will probably reply, okay, I want to create a new sales quote or a sales order, just click on the new button, and so forth, right? So here's an example of, a little bit under the hood of that works. So this is basically the page description, as you can see here. So it's not a complete one, but just to give you an idea what it looks like. So it has, I know it's a little bit unclear, but basically what it says, this is basically the role center. So you have some actions here. It says, for example, sales order, description, view the existing sales order, sales quote. These are the actions that the agent sees, and they're all the fields and so forth. So that's what we basically show to the agent. And we tell the agent, here are the available functions. So you can end the task, you can draft a reply if it's time to write a mail, or you can request assistant, request review, set field value, and so on and so forth. So these are the possible actions that the agent can take. And then the LLM replies, at the very beginning of the flow, okay, navigate to this node, which is, the name contacts, because I want to find that person with that contact. So that's basically, the principle of it. So this is how our agent work. So that's how the platform works. But as you can see, it's very powerful because it's doing everything through the UI. So I thought I wanted to give you a little bit of insight on how that works. I can see I'm running out of time. So thank you very much for attending the session. We won't have time for Q&A, but just feel free to catch me at the booth or anywhere in the conference. I hope you enjoyed the session. Thank you very much for attending.